So, but fructose can be, of course, obtained from diets with large amounts of sucrose. We know that sucrose is made up of glucose and fructose. So if you have high intake of sucrose, you're definitely going to get fructose to some extent. And we have things like honey, we have things like corn syrups, where there's quite a large number of fructose. And therefore, which means in our diets, we more or less encounter fructose. And we have to find a way of utilizing fructose so that then gives us or forms as a source of energy. And again, this metabolism majorly occurs in the liver, where fructose is converted to fructose 1-phosphate with the help of an enzyme called fructokinase. And fructokinase still can be found in the kidneys and the intestines. Just like we saw in the other process when you're converting glucose 6-phosphate to glucose, that can also happen in the kidney, it can also happen in the intestine, but it's mainly happening in the liver. So what happens is that once you have fructose and it gets to the liver with the help of the enzyme called fructokinase, it's going to be converted to fructose 1,6-phosphate. Then another enzyme, an aldolase B, or rather we call it fructose 1,6-phosphate aldolase 6, converts fructose 1-phosphate to dihydroxyacetone phosphate. Of course, we know what DHAP is, and glyceraldehyde. Okay, fructose 1-phosphate can be converted to glyceraldehyde. This is not glyceraldehyde 3-phosphate. This is just glyceraldehyde. Yeah? So that is done by an aldolase B. Now, we know that in glycolysis, we require glyceraldehyde 3. And we also know that we can convert dihydroxyacetone phosphate to glyceraldehyde 3, the enzyme that converts DHAP into G3P. In full, it's referred to as triose isomerase. Triose isomerase, or TIM. Sometimes it's called the TIM. Okay. So I can see quite a number of you have got it correctly. Sorry. So in this case, the aldolase is giving us DHAP and glyceraldehyde. Then glyceraldehyde is converted to glyceraldehyde 3-phosphate by triose kinase. And of course, once you have this glyceraldehyde 3-phosphate, you can still convert this into glyceraldehyde 3-phosphate, and together they can be converted to glucose. Okay, we know that either if you have G3P or any intermediates within the glycolytic pathway or the Embeden-Meyerhof pathway, any intermediates can be converted back to glucose. We know that. So from here we can form glucose, but from here we can also produce pyruvate and energy, of course, ATP in form of ATP. So there are two pathways that this can take, either to generate glucose or they may be oxidized in glycolysis. And of course, we know what happens once we have glyceraldehyde 3-phosphate or DHAP. We know that we can still produce two pyruvate molecules from either of these molecules, and of course with ATP in general. So just to ensure that we understand this again, the utilization of fructose by fructokinase, then aldolase, can bypass steps of glucokinase and PFK, which are usually activated by insulin. So we can also, of course, this bypass glucokinase activity, which is MPFK. And we know that that is step 1 and step 3 of glycolysis, if you remember that. So we can bypass that with the action of fructokinase and aldolase B, of course. So this would be the reason why many patients who are diabetic do not have fructose in their system. It's because of the action of fructokinase and aldolase B, because they are bypassing step 1 and step 3 of glycolysis, if you remember that. So precisely this is what is happening here. We have fructokinase producing fructose 1,6-phosphate. Then with the action of an aldolase, you get glyceraldehyde and dihydroxyacetone phosphate. Then, of course, with the action of triose kinase, of course, with the requirement of ATP here, you're going to generate glyceraldehyde 3-phosphate. And with the action of the isomerase, what we refer to as triose isomerase, you're going to get, again, glyceraldehyde 3-phosphate. So once you have this, then you can decide to either go through glycolysis or gluconeogenesis. So you can produce glucose from gluconeogenesis, or you can produce pyruvate from glycolysis, either way. So that is how fructose is metabolized. That is how fructose is metabolized. So the end product of fructose metabolism, once you get it in diet, is you're either going to get glyceraldehyde 3-phosphate, not glyceraldehyde 3-phosphate, you're going to get, glyceraldehyde 3-phosphate, that's the ultimate end product. But before you get there, you're just going to get glyceraldehyde and dihydroxyacetone phosphate, which of course can all be converted to glyceraldehyde. If it's in the muscles, now we saw that that is happening in the liver mostly, but in the muscles, we have hexokinase, and hexokinase can phosphorylate fructose to fructose 6-phosphate. And we know that fructose 6-phosphate is an intermediate in the glycolytic pathway. It is an intermediate in the glycolytic pathway. So once you have fructose 6-phosphate, again, you can still undergo glycolysis to get pyruvate, but you can also undergo a reverse of this so that we undergo what we call gluconeogenesis to generate glucose. So it's also possible to go either way, but this is in the muscles. So in the muscles, fructose can very easily be converted to fructose 6-phosphate, and we know what happens to fructose 6-phosphate. Fructose 6-phosphate can be converted to fructose 1,6-bisphosphate, and splitting happens so that we get DHAP and glyceraldehyde 3-phosphate, and then of course they are all transformed all the way to get to pyruvate. Or you can bypass step 2 to produce glucose 6-phosphate. Step 3 to produce glucose 6-phosphate, and then glucose 6-phosphate is converted to glucose. But something to note here is that hexokinase has a very low affinity for fructose compared to glucose, and therefore this might not necessarily happen in the muscles per se. That's why we said that metabolism of fructose is majorly occurring in the liver, seen it in the liver, but as we've seen, the kidney can also perform this, and the intestines can also be a key place where this is happening. Yeah, but we can also convert fructose 6 to glucosamine 6-phosphate, which is a precursor of amino sugars. Yeah, but for us, that's not very important for us. All we're key in seeing that. Now, specifically in the testes, fructose is converted into glucose through sorbitol formation. And this requires an enzyme called aldolase reductase and sorbitol dehydrogenase. So in the testes, something else is happening. So it's another pathway called the sorbitol pathway. And not so these are other minor pathways that we didn't want to get into. So sorbitol pathway or sorbitol formation will enable fructose to be converted into glucose. And so that's the reason why deficiency of fructose causes male infertility. So if an individual, say, is born with mutations that affect fructose metabolism in the body, and that individual is male, then they are likely going to suffer from infertility because of the deficiencies in fructose, which can be utilized, of course. Now, I don't want to go into diseases associated with fructose metabolism. I'll jump that. I have a whole lecture for diseases associated with carbohydrate metabolism, which we'll look at in details, or rather you can read on your own.